Okay, let's take a look at our lesson for today. We're going to be looking at definite integration. Before we start, I actually want to go back and talk about what we've done so far. So we first learned about indefinite integrals, and when I was explaining those, I was basically telling you that they don't have numbers on the integral sign, right? There aren't any numbers on there. Definite integration is, there's numbers on here. That's really the only difference between the integration that we did and the integration that we're going to do, is it actually adds another element to it. So we talked about indefinite integrals. On the first day, we learned how to integrate using formulas. And then on the second day, if you recall, we learned how to integrate using U substitution, which is a huge, huge technique for us. Then the last lesson was when we learned about Riemann sums, approximating area under the curve. And we started to get into, well, what are we actually doing when we're finding the area under the curve? Is it geometric? Are we just finding geometric area, or is there some application? Like we were looking last time at speed or, distance, things like that. So we're getting more into uses for integrals. So that brings us to today, where we're going to actually talk about definite integration versus indefinite integration. So let's take a look at this little diagram right here. A lot of the stuff we've already talked about. We know that this is called the integrand. We've talked about that before. This tells us which variable to integrate. We've talked about that before. The new things for today would actually be these locations right here. This is called the lower limit of integration, or the lower bound, and this is called the upper limit of integration, or the upper bound. So those really are the new things for us for today, is that we're actually going to have numbers on the integral sign. So what does that mean? So we have a couple of pictures underneath to try to describe what that means. So I'm not sure if you can see this very well, but this is the integral from a to b of f of x dx. But basically what we're doing is we are calculating the area under this curve, starting at a and going to b, and basically all of it right until we hit the x-axis. That's the geometric area that we're going to calculate with this integral. And today we're just going to talk about it geometrically. We're not going to talk about applications of it, just actually the physical geometric portion of it. So that's what we're looking at when we look at that integral. Notice that these are x's and my bounds are x bounds. Pretty significant for us. Because if you look at the next picture, this graph, these are y's, and my bounds are y bounds. We are really, over the years, we've become very comfortable with graphing things with respect to x. That's our norm. And when we have to graph with respect to y, it's a bit challenging for us. And so it's something that we really need to work on being able to see it that way. It's going to be a good skill for us. So here on this one with x's, we are looking at the curve and down. That's the area that we're going to be calculating. With respect to y, we're looking at the curve and not down, but left. Okay, because if you think about it, this is the higher that you go, the larger those y values get, right? In this respect, basically, the farther right you go, the bigger the x values get. And so we're actually calculating this way versus this way. So it's just something to start thinking about. We have some rules to go over. So our first one is on order of integration. Now normally, not always, but normally, this lower bound is a smaller number than the upper bound. That's the norm. Let's say it's not written that way and you want it to be, or you want it to be written a different way. There is a rule for that. We are allowed to change the order that we integrate, to change these bounds, if we do the opposite. So basically I can reverse the order. I can change this instead of from b to a, from a to b, as long as I take the opposite of my integral. So that's a new rule that we have to talk about. This one, the zero width interval. So what we're doing basically is we're accumulating area as we're going along. If you look at this, we're starting at a and we are accumulating area as we head towards b. If we start at a and end at a, have we accumulated any area? No, right? That's called the zero width interval. And basically the answer to that integral is 0. We don't have any area that we have accumulated when we start at A and end at A. So that's, kind of can be beneficial to us. Number 3 and 4 are ones we've talked about already. We certainly can take the constant and pull it on the outside and then integrate and then apply the constant. Or on number 4, we are allowed to split it by addition and subtraction. That's an okay thing to do. So we've talked about that previously. The other new one for today is, it's called this one right here, the additivity. And what I like to do, you know me, I need to see it. So let's kind of get a picture of what's going on. What this rule is telling us, that if I integrate between A and B, and I add to that the integral between B and C, that I will get the integral from A to C. So it actually allows us to split the integral using the bounds, different bounds, and that's okay. Okay, we okay with that? All right, so that's an okay thing to do. And it's going to come in handy to us later. All right, so now let's think back. So I'm getting ready to go over scary Riemann sums. I'm just going to introduce scary Riemann sums, and you're thinking, what? She's crazy. So the regular Riemann sums that we did like a day or so ago with the rectangles, I'm hoping nobody in here thinks that was scary, right? That was not scary. It's just finding the area of each of the little rectangles and adding them up. We're okay with that. And I'm really pointing this out because after I talk about this, and we actually have a lesson on scary Riemann sums, students tend to go to that. Even if I just want regular Riemann sums, they always go to the scary Riemann sums. So I guess because they're so traumatizing, I don't know. But I want to explain the difference, what we're talking about. Remember when we learned how to use the definition of the derivative? Remember those days? Right, the days of definition of the derivative where we did the limit, we were all happy, yay! And then we learned how there were rules that were much faster. We were like, oh wow, that was a really long thing to do when I have a rule. Well, that's kind of where we are with this scary Riemann sum thing. This is actually the definition of an integral. What's the definition? Doing the limit as n approaches infinity of Riemann sums. Let's think about that for a second. We did talk about the fact that the more rectangles we use, the more accurate our estimate is, right? If it was possible to use an infinite number of rectangles, we would have a perfect value for the area. Right? And that is exactly what's happening here, is we're doing the limit as n goes to infinity of the scary Riemann sums. Okay, so if we were sitting in a college class, your professor would probably be really excited about this, and would probably want to spend the entire period doing these problems, right? So, but for us, though I like to give you a little taste of college type calculus and AP calculus, we really don't have time. I know, don't be upset. We don't have time to do the scary Riemann sums full out. I mean, do you think about how long it took you with the definition of the derivative? Can you remember that time? Like multiply that by 3. Okay, and that's where we're talking about how long it would take us to do one of these by hand. So what we do need to know, I'm just telling you, what we do need to be able to do on the AP test is be able to go back and forth between this version and this version. We need to be able to translate from one to another. That's all we need to be able to do, and I actually have a whole lesson on that in a few lessons down the line. I just wanted you to know about it and have it in your mind so that when we do that lesson, it's not so scary. It's just a definition of an integral, is all it is. Okay, and we're not going to actually do the full out definition of the integral. All we're going to do is learn how to go from one type of notation to the other. That's it. We're not going to actually calculate the scary Riemann sums. Yes? I would wait till we do the lesson, yeah, for sure. That lesson is, pretty intense, and I'm going to wait till after that. The things that we're covering today aren't going to be on tomorrow's formula quiz. Okay? All right. Any questions about the concepts before we jump into the problems? So today what we're going to be doing is we're actually going to just calculate area geometrically. It's really using geometric formulas. Tomorrow we're going to learn about the fundamental theorem of calculus. Doesn't that sound really important? Fundamental theorem of calculus, right? That is where we learn how to do definite integrals like by hand, the algebraic technique. That's what we learn. Today we are going to do definite integrals, by hand, but we're going to use geometry. And even when you learn the fundamental theorem of calculus tomorrow, if it's a perfect geometrical shape, you should just do it that way. Because it's faster, it's quicker, it's easier. But of course, it only works if they're perfect geometric shapes. It's not going to work on a curve. So let's take a look at our first one. We are looking at this one right here. So we're going the integral from 1 to 6 of 4 dx. Let's think about what that 4 means. It really means, if we take it out of the context of the integral, that's like the y equals 4 line. That's what we're looking at, y equals 4. And so we are with respect to x. So we have x bounds. So I'm going from 1 to 6. And the line that the equation is y equals 4. So we're going to draw basically that horizontal line. And all we're doing is finding the area of that rectangle. Okay, even when you learn fundamental theorem tomorrow, it's much easier to do this integral with a rectangle, just finding the area of the rectangle. So the difference between here would be 5. So it would be 5 times 4, or 20. Now, just so you know how to check your work, I'm going to show you how to do integrals on your calculator, just for your benefit to check your work. We're doing everything by hand at first, but eventually we'll get to where we use calculators. So if you have your calculator with you, just for demonstration purposes, if you would get that out. Okay, so what we're going to do is we're going to calculate that same integral that I just did, but we're going to use the calculator to do it. Now, most of you were in Pre-Cal Pre-AP, and you would have done this probably in the graphing section. I recommend not the graphing section, but just a clear screen to do your integral in there. And so remember the Math 8 we've been doing for a while? Math 8 is the derivative. Well, Math 9 is integral. So we're going to do Math 9. And if you have the new operating system, it should show up like this. If you don't have the new operating system, you should get it, because your input is much quicker with the new operating system. And you can ask me about it if you would like. So I'm just going to enter that integral that we just did. That was from 1 to 6. And it was 4. And then it was dx. And so what the calculator did is it calculated the integral for us, and it's 20, which we already knew because we calculated it. Now I want to give you just a little bit of caution about your calculator. Okay, you are smarter than your calculator. I'm telling you that because sometimes what it's doing, it's running an approximation program, kind of like the Riemann sums. It's not Riemann sums, it's a little bit more complicated than that, but that's what it's kind of doing for you. It's not really doing the integral like we are. It's not going to really do, like tomorrow, the fundamental theorem. It's not really doing the fundamental theorem. It's doing an approximation program. So especially when you use radicals, like when you're integrating a radical, it gets a little confused. Like say your answer is 7. Say you integrated the radical by hand and your answer is 7. It could very well probably come out with an answer of like 7.000025 or something. It's because it's using an approximation program is why. So if you see that, don't be alarmed. It's just that you're smarter than your calculator. That's the only thing. So don't worry about that. It's just it can't handle specifically like radicals very well and some other things very well with its approximation program. So that is how you use the calculator to check your work. Checking. Okay. You can go. There we go. So let's go to our second problem. So here we have the integral from 1 to 3, and this is the line x plus 2. All right, so we're going from 1 to 3. So let's do that. So we're going from 1 to 3. And, you could graph the whole line if you want to. I typically just graph the portion that I need. So I would just put a 1 in here. So 1 plus 2 is 3. So it would be at 3, and then I'd put a 3 in there, so 3 plus 2 is 5. So I know that it would, look like that. And so basically it's making a trapezoid for me. That is the area that I'm going to find, the area of that trapezoid, which we've been doing a lot with, right? We now should know the formula for the area of a trapezoid: 1/2 base 1 plus base 2 times the height. And for our problem right here, we would have 1/2. Let's see, our base 1 would be 3, plus our base 2 would be 5, and the height would be this, which would be 2. So we do all of that arithmetic, and we get 8 as our answer. Okay? So again, we're just doing this geometrically. We have a perfect geometric figure. Why not use it and just calculate the area that way? This one, this problem right here, actually a lot of students look at it and really don't recognize what it is geometrically. I would like for you to get to where you can recognize what it is geometrically, even when we learn how to do this with a fundamental theorem. And actually this particular problem we won't be able to do with the techniques we're learning in AB in Cal 1, but in Cal 2 we could have some fun with this problem. I'm just saying. It would take a while, but it would be pretty fun. And if you know that it's, well, what we're getting ready to say it is, let me show you. So I want you to think about this and relate that to what you see. So what does that represent? It's a semicircle, right? It's solved for y. So it's not the plus minus. It's not both halves of the circle. It's not the whole circle. It's a semicircle. And it's the positive part which puts it here. Okay? Now, if it were the negative part, if there were a negative in the front of here, it would put it underneath. Right? You with me? Because it matters. It does matter where it is. So this one is here. So this is really just finding the area of a semicircle. Way easier than any other technique that you could use. So let's do that. So it'd be, it's a semicircle, so it's 1/2 pi r squared, and we know that r happens to be 2. So 1/2 of pi times 2 squared is 2 pi. So that's the area of that. Okay, we okay with that? So then we need to just recognize, if I'm integrating from, a radical of 1 minus x squared, that's just a semicircle with radius 1, right? So we just need to recognize that. That's something on our list. All right, this next problem that we're going to look at actually is the first time we're going to talk about area that's underneath the x-axis. Up until now, we've only talked about area above the x-axis. Now, the area itself really truly isn't negative. I mean, we don't really have negative area, but when we're doing calculations with this integral, it's going to act like it's negative area. It's going to change the sign. So if it's underneath the x-axis, it's going to have a negative associated with it, a negative value associated with it. If it's above the x-axis, it's going to have a positive value associated with it. And so let's do that. Let's calculate. We need this. So we're going from -4 to 4, which is from here to here. And so I have these pieces to calculate and this piece in the middle. Okay, so we need to find all of that area. So I'm just going to do them one triangle at a time. I'm going to work on this one first. And it's going to be negative, again, because it's underneath the x-axis. So let's see, our formula is 1/2 base, 3 times height, which would be 2. Okay, so that's going to be that, the area of that triangle. So this one is on top above the x-axis, so it's going to be positive. So this one is going to be 1/2. Let's see, the base is 3 and the height is 3. Okay, and then this one is underneath, so it's going to be negative. So 1/2 and the base is 2 and then the height is 1. Okay, so combining that all together, adding that all together is going to give us that entire integral. So this gives us, what, -3. Then we add, what is that, 9/2. And then we're going to subtract let's see, that's a 1. So I do my arithmetic, I combine combine those together, and I find the total integral is 1/2. Okay, are we okay with that? Mm-hmm. No, you don't have to. I just did one. You can do one, or this middle one, I just did this one big. But really, the way you split it up is totally up to you. However you want to split up the area. Okay, the next problem is totally abstract, because that's, of course, we have to do that too. So let me get some room over here. What we're given is just some values of some integrals. And so we're told that from 0 to 3, that integral value is a 4. And you know me, I'm real visual. I have to see it. I have to write it out like this. You don't have to. I'm just showing you what I would do. And then from 3 to 7, that is -1. And that just kind of helps me visually know, because there's some crazy things that they're going to do with these. All kinds of different integrals that they're going to create with something like this. And so it would be really helpful for you to get a big picture of what's going on when they start adding, subtracting various different things. So it just, it's helpful to me. So, okay, here we go. So our first problem, integral 5 to 5. Well, luckily for us, that's a 0 width integral, right? Because we don't have any information about 5 at all. So from 5 to 5, that's 0. That's from a rule that we know. The next one, we are not told what the integral from 0 to 7 is, but we can figure out what it is by doing one of those rules, right? So we're going to split it. We're going to go from 0 to 3 of f of x dx plus, so we're using that fifth rule that we learned today, right? We're going from 3 to 7 of f of x dx. So I'm splitting it because that's the way that it's given to us. That's what we know. So now I can just use substitution and substitute 4 for this integral from 0 to 3, and then substitute a -1 for this integral from 3 to 7, and that gives us our answer of 3. Okay, are we okay with that? Of course, we'd have to show our work, because just writing the number 3 down there has no meaning. You need to show the calculus behind it. The last one, they're asking, so this is a little weird. We have this 2 in here, but we're going to use a rule, right? We don't have many rules. We're going to use them when we can. So we're going to take the 2 and pull it outside. So this is the same thing as 2 times the integral of 3 to 7 f of x dx. So it's 2 times, and we know the integral from 3 to 7 of f of x dx is -1. So that gives us a -2. Okay, how are we doing? The last one is actually with respect to y, and I'm doing this on purpose. We really are, I know, most of us are probably fairly uncomfortable graphing with respect to y and working things with respect to y. It's something that we kind of need to just jump in and embrace. Yes, there are ways to do it to avoid it, but I don't want you doing that. I want you to graph with respect to y, because it's going to be really helpful to you when we move into area and volume and such with respect to y. So I just really want you to think with respect to y here instead of trying to avoid it. So up here, when we were working this problem, this really would have been like y equals x plus 2, right? Isn't that what we graphed? We graphed the line y equals x plus 2. Okay. So when we're here looking at this kind of problem, this is actually like x equals y minus 1. That's what this is like. Okay, just like this was y equals x plus 2, this is a little different. Now, if you want to graph the whole line, certainly you can solve for y and graph the whole line. That's fine. That's not a problem, because we're used to graphing, y equals, not x equals. But what our purpose is just really to draw the portion that we're going to find the area of. And so I'm really not going to try to draw the whole line. I'm only going to be worried about the part that are in this interval from 1 to 4. And these are y bounds. They're going to be on the this y-axis, not the x-axis. So I'm going from 1 to 4. Okay, so I'm thinking in reverse again, but how we normally do. So when y is 1, my x value is 0. So when y is 1, x is 0. So we're right there. Okay? So when y is, and since we know it's a line, I can go straight to when y is 4. when y is 4, so 4 minus 1 is 3. So we're here, and this is my line. Now we probably really want to draw down. I know you probably just really want to draw down and find this area. If you do that, you're going to be finding the wrong area, and you're going to get the wrong number, wrong answer. This area is not what we're looking for. We're actually looking for this area. And you can tell that those two shapes are completely different. Right? They're completely different shapes. This shape versus this shape. So it's really important, again, it's really important for you to start thinking about in terms of y. It really will be helpful to you. So we're going to calculate, this is just a triangle like, the other triangles we've been working with. We're going to calculate it the same way. So 1/2 base, well, that difference is 3 times the height. That difference is 3. That's 3. So our answer is 9/2. Okay, and that's our very first integral with respect to y. How are we doing? We okay?